Hey guys, for this lecture what I'm going to talk about is I'm going to do momentum and collisions examples. So last time we talked about what momentum and collisions, or what momentum is, impulse, and how we can use that to solve collision type problems, whereas we couldn't do that type of stuff before. So I've got an example already up, and it is, what is the momentum of a 10 kilogram cannonball moving at 20 meters per second? So we usually start with the simplest type of example, so once again we'll do just that. So momentum is equal to mass times velocity. So we have our mass right here, 10 kilograms, and we have our velocity at 20 meters per second. So we plug that in. 10 times 20 is 200. No, 220. 200 kilogram meter per second, which is momentum's units. And that's that for that type of problem. So pretty easy, not too difficult. You just kind of plug it in. All right. Now let's get to another type of problem you might see. A 5 kilogram ball is dropped from a height of 10 meters and it rebounds to a height of 8 meters. What impulse was given to the ball by the floor? Okay, so if you remember, we want to know what impulse was given to the ball by the floor. If you remember, impulse is force times time, but we don't have any of that, right? So we have none of this. But impulse was also equal to the change in momentum. And the change in momentum, is equal to the change, mv final minus change mv initial, right? Or not change on those. It's just the mass of the ball initially, or finally, minus the initial, okay? And so if we want to figure this out, if we want to figure out the change in momentum, which is the impulse, we need to figure out the velocity before and after. We have the mass right here, 5 kilograms. So we need V final, we need the final velocity to find impulse. Okay. But all we have are the heights. So we have heights, but not the velocities. So what can we do here? Use energy. Okay, so we can use energy here to solve for velocities. Okay, so we have a height of 10 meters for the first one, 8 meters for the second one. So what we can do is, you have the ball, and it's above the floor, right? And it's a height of 10 meters. Okay, and so it's going to be dropped that way. Okay, and then what will happen is it will rebound to a slightly less height, 8 meters, and the velocity will be in a different direction. So we need the energy at this point and energy at this point. So this would be the initial energy. This would be the final energy. So at its highest height, E initial equals mgh, right? Where h is 10 meters. And then E final, it will equal the same thing. And then what we can do is we can set that equal to the point down here and the point right here where it's moving, or just before it hits. So right here, this is just and it will only have kinetic energy at that point. So we can set E initial equal to the initial kinetic energy. And here we could do the same thing, okay, where it's just after it hits. and it will have KE final down there. So we can do E final equals KE, okay? So we set MGH equals 1/2 m V naught squared. This is what we need to solve for right here. And then we can do MGH. I guess I should set that as 1 and 2 just so there's no confusion there. And this will be equal to the final, right? So we did this in energy problems, you know, where we set, you know, if you drop a ball, right, it's going to transfer its gravitational potential energy all into kinetic, okay? So we can cancel the m's. We can do that in both problems, okay? So GH equals 1/2 V naught squared. GH2 is 1/2 V final squared. We just need to solve for V, right? So V naught, if you multiply the 2 over and take the square root, it's 2 GH1. Here, you can do the same thing. Oops, trying to do too many things at once. Okay, so the numbers on that are this, the initial energy is equal to the initial moment, velocity is equal to 14 meters per second, and the final velocity is 12.52. Okay, so now we have our initial and final energy. So now our change in momentum is equal to the mass of the ball, which I think was 5 at this point, 5. So P final minus, I keep doing the same thing. P final minus P initial, right? M V final minus M V initial. We can pull out the M. And we can do the math on this now. So it's 5 kilograms, 14 meters per second, minus 12.52. And what we get with this is 100. Oh, one thing I should mention is that since, one thing I forgot to mention here is our initial velocity, so we have to set a direction, okay, which I forgot to do. So we need to set a direction because I forgot to do it, because velocities have a direction. They're a vector, so set a direction. Let's say up is positive. This means that V final is positive, V initial is negative. So this means that when we plug these numbers in, so now we have 5 kilograms times V final was 12.52 minus a minus, okay, because that was now coming down. So now you're going to add those and multiply, and you get 132.6 kilogram meters per second, which is the impulse. Now, if you wanted to, you could have set down as positive, and if you had done that, you would have gotten a negative number here, which isn't a big deal, okay? You really need the magnitude of the impulse, okay? So that's that problem. The main trick here is when you're doing impulse, you either need to be given force or time, or you need to be given the change in momentum somehow, which is kind of tricky in this problem because we didn't know about the velocities. But you could use energy because you had potential energy here and here to get those velocities. Okay, so kind of tricky, not too bad. Certainly, you know, more challenging than the first one. Okay, so now this next problem is kind of an interesting one. We don't do too many problems with varying forces here. Most of the forces that we get are pretty constant, and that's because dealing with anything that's changing is difficult. But let's read this. A varying force of magnitude shown below, so I'll be giving you the graph on how it varies, acts in the x direction on a 2.7 kilogram particle. And we want to know, what is the impulse given to the particle by the force? So once again, we need impulse, right? So these types of examples, or these types of problems, are kind of set up like this, where you'll be given, if it's a varying force, you need to be told how the force is changing with time. And so I'm just going to set up a really quick little graph to show you how it's changing with time. Jeez, I need to like, ugh. Okay. For some reason, it's more challenging to make vertical lines than it was to make horizontal. Okay. So force in newtons, time in seconds, and the time is going to be 1, 2, 3, 4, up to 5 seconds. The force will be in 1, 2, 3, 4 newtons. Okay. Let's go ahead and plot this thing. And what I have is the graph doing basically this. I need to, oh. What? Oh, I know what I did wrong. Okay. I need to add one more, where this is the 0. There we go. Okay. So for the first two, the force is increasing. Then it holds constant for the next second. Then the force is decreasing. So this would be equivalent, like you're slowly increasing your force on something. Then you're pushing constantly. Then you're still pushing it, but you're kind of pulling back on how you push it. And these are all, you know, should be straight lines, right? But I'm kind of sucking it up on that and being able to draw that. Okay, so we need impulse, right? So we need impulse. And again, impulse is force times time. And we actually have these, right? We have the force numbers and we have the time. But here's the thing. Because it's varying, okay, to get the actual force, you'd have to take, you know, how much force is at this point, like right here, this little section, multiplied by the time, duration, then do it here, and here, and here, and here, and we'd have to add up all of those little points. An easier way to do it is to take the total force, or to take the force per time, per change in time, by finding the area. So we can add those up by doing the area. So we can find this from the graph by calculating area under the curve. So adding up those little bits, like I just said, is equivalent to doing this, okay? It's what's known as finding an integral, actually. So how we can do this, okay? This straight line, right? Because it's pretty obvious, these boxes are all filled in. And so the length of this box and the width of this box and the height of the box is both 1. So it'd be 1, 2, 3, 4. Okay, cool. So that's 4. But then we have these issues of like these like triangles, and we don't really know how to do that. So I mean, we could find like this, like we could find triangles here and try to pick them out and get the area that way, but it's still pretty hard. But if you notice something, what's going on is we're moving over 2 seconds, right? And then in the span of that, we're going up to 5. So this whole area is 1, 2, 3, 4, 5, 6, 7, 8. It's 8 total boxes. But we're not actually filling up the entirety of it. We're actually filling up, if this is a true diagonal line here, we're filling up half. So if there's 8 boxes here, and then 8 boxes here, okay, the total number is 16 boxes. But we're actually filling up half of that. So we'd fill up 8. Okay, so this would be 4 boxes for the middle section. And then half of 16 boxes for the diagonal sections. Because it's only, we're only doing half, right? We're cutting it in half. That's our triangle, right? It's 1/2 base times height. So what we do then is 4 plus 8, which is 12. So 12 kilogram meter second is total impulse. Or you can write this as 12 Newton seconds. Okay? Either way, or Newton per second. Either way, it's the same thing. Okay? So that's the answer for that guy. So if you see a varying force problem, all you got to do is add up the area under the curve. Okay? Next up, we're going to start collisions. So in this example, we've got 2 train carts that are on a collision course. One train cart is moving at 20 meters per second. It is 100 kilograms. The other train cart, also 100 kilograms, isn't moving. So how fast will the train carts move together after the collision? Okay, so how this looks is what, for every single problem, every single momentum problem, what you want to do is set up a before and after, or 2 states like we did with energy. So for momentum problems, set up a before collision and then after collision, and find momentum in each section. So what that means for this is we have a train cart that's moving. Okay, it's got mass m, it's moving with velocity v. We've got another train cart that isn't moving, but it still has mass m. This is our before case, before the collision happens. Afterwards, we have these 2 train carts that are moving together with velocity v, and they both have mass m, okay, because they're going to collide and then they'll move together afterwards. Okay, so P initial, momentum initial, is mass times velocity of the first cart. I'll just do initial v, plus m times v, which is this case equal to 0. Okay, so that guy goes away because it's 0. P final after the collision is m plus m, because they move together, times the final velocity. Okay? So, what we then do next, set the momentums equal and solve. And we want to know, we're actually solving in this problem, how fast will the train cars move together after the collision. Okay. So we set P initial equals P final. P initial was just mv naught because it wasn't moving. The second one wasn't moving. Oops. And then the second part was just m plus m v final. We can do a little bit more without the math here, or without putting numbers in. So m plus m is 2m v final. We can now cancel the m's because they're the same. And what we'll see here is if we divide over, v final equals the initial velocity over 2. And the initial velocity was 20 meters per second, I believe. Yeah. And that's divided by 2. So they'll move together. Here, they'll move together at just 10 meters per second. And if you think about it, that actually makes sense. So typically what happens is there's a trade-off, right? As you increase your mass, your velocity has to go down if everything's conserved. So our mass doubles because we're 2 train carts now, so our velocity would decrease by 2. If it was times 3, it would decrease by 1/3. Times 4, decrease by 1/4 is what you'd expect to happen. The only other thing for this type of problem, and this was a one-dimensional problem, is that we solved it with inelastic collisions, or we solved it as if it were an inelastic collision. Unless you're explicitly told that it's elastic, like you have 2 elastic balls, 2 rubber balls, there's some hint that it's an elastic collision, don't treat it as an elastic collision. Treat it always, baseline, as an inelastic collision, unless you have reason to believe that it's an elastic collision. In other words, we're not going to conserve kinetic energy here, but you can always conserve momentum. So you always want to start with that as your baseline, okay? And this type of setup where we do the before and afterwards, before and after the collision, that's basically how all these collision problems work with momentum. Similar to energy, right? Where you have the energy before, or energy 1, and then energy 2, and then you set them equal. Okay, works the same way. Very similar process. Oh man, I forgot that when I did this, my notes, I give these guys like happy faces. Except this guy who's sad because he's about to get hit. But then they're both happy afterwards. Okay, anyway. Sorry, I'm a dork. Okay, next up, we've got this problem. So we want to calculate the recoil velocity of a 5 kilogram rifle that shoots a 0.02 kilogram bullet at a speed of 620 meters per second. So I don't know if you've ever shot a gun or done any type of ballistic stuff like that, but if you're shooting something, right, like even like a cannon or whatever, it will recoil, right? It'll move backwards. So this sort of problem isn't a problem where you have 2 things that are colliding and then rebounding. This is something where you have 2 things together that are then separating. It's almost, and you know, it works similarly to an explosion problem where things are exploding apart. And so you can use collisions to figure this out too. So what we need to do is, again, step 1 before So step 1, before and after. Okay? So we have our before case, and we have our after the collision. Okay. Oops, that's a really poor, good enough, whatever. Okay. And I apologize for my drawing capabilities here. That's kind of a rifle, I guess. Let's move that guy up there. Okay. That's our bullet. So this is, we'll just call our bullet MB. So bullet, mass of the bullet. This can be MR, or I'll just call it mass of rifle, so rifle. And then what happens afterwards, don't have to draw it twice. What happens afterwards is the bullet will then be shot, move at velocity v. Still have MB. Oops. And then MR. Okay. So now we need to figure out our momentums. So P initial. What's happening initially? Nothing. You're not shooting the bullet yet. The rifle's not moving. It's just 0. You have, the mass of the bullet times its velocity, but velocity is 0. So we don't have to worry about that. But P final is actually going to be composed of a couple things. It will be composed of the mass of the rifle, and the rifle's going to recoil, right? With VR. So we're going to call this MR VR plus MB, and this guy will move forward, VB. Okay. And so what we do is now we set, so step 2, we have our momentums. Set P initial equals P final. And in some books, even in my notes online, I sometimes use like I for initial. I'm just using O in case the notation confused you. So 0 is our initial. Our final is MRVR plus MBVB. Okay. And we needed, what did we need? Calculate the recoil velocity of the rifle. So we're actually solving for VR here. So we're going to move the bullet over. I don't know why it's so difficult for me to write right now. Negative, because we're subtracting it, equals MR VR. We're going to divide by MR. MB VB over MR equals VR. And we're going to get a negative value here, which denotes that the rifle is moving to the left. Okay. Or the opposite of the bullet, I should say, because we haven't defined direction yet. I should probably be defining direction more often than I am. What am I doing? Okay, so negative 0.20 kilograms. 620 is the velocity, and this is over 5 kilograms. So you got this tiny number times this massive number over that regular number, and we ended up with a relatively normal number. Okay, so minus 2.48 meters per second. And again, this minus denotes a velocity in the opposite direction of the bullet. Okay? And that's to the left in our case because of how I drew the problem. All right. the next one that we're going to do is about billiard balls. There's really not too many varieties of problems that come with this. I mean, there's some. We're covering most of them. Okay. Billiard ball A of mass m is moving with speed VA, okay, and it collides head-on with ball B, also of mass m, that is at rest. We want to know what are the speeds of the two balls after the collision, assuming it is elastic. Okay, so now it tells us it's elastic. So now we have to deal with an elastic collision here, okay? It's still one-dimensional. Remember how I said don't assume that something is elastic unless told. Also, don't assume something is two-dimensional unless you're told. So we're going to do the same thing we always do before. And after. Okay. So we're told that we have billiard ball A, okay, moving with VA. Oops. Okay, and it's going to collide with B. They're both mass m. I should have drawn the smaller to be, you know. Okay. Oof, that ball is ugly. Oh my god. Just B. That's close enough. Okay. And then afterwards, we don't know what's going to happen. I'm going to give these guys subscript of final. Initial that as well. We do know that VB initial is 0 because it tells us it's at rest. Okay. So yeah, we have no idea of the direction or any of this, what's going on afterwards, but that's what we're trying to find. What are the speeds of the two balls after the collision? Okay. So we need to do P initial and P final. So this guy, MVAO. Okay, and then that guy's 0. That's our P initial. Our P final is going to be MVAF plus MVBF. We don't know if they're moving. We don't know anything about them, so we write that. Okay, so now what we do is we set initial and final. Since it is elastic, we can do energy this time, but start with momentum, always, okay? It's an easier problem or an easier equation to work with. We can cancel all the m's. Okay, so now we have this going on. But we have two unknowns, right? We have this is unknown, and VBF is unknown. Two unknowns, one equation. We need another equation. So use KE equation now. Okay, so because the masses are the same, I'm using that other equation that we derived here, where the initials are equal to the finals in this way. Oops. The VBO was 0 because VB was at rest, right? And if you're curious about, it was a negative sign parentheses on the original equation, I just distributed the negative and you get this guy. So now we have VAO equals VBF minus VAF. Okay, so this is equation 2. So now we have 2 equations. We have VAO equals the 2 added, and we have VAO equals the difference of the 2. So what we can do is add them, right? So let's just add the equations. So you get 2 VAO. So, I mean, you can also just plug in, right? I could have taken this, plugged in for VAO here. It's however you want to solve it. You have 2 equations, okay? And you need to solve for it however you want. So you can solve for VAO in one, plug in, solve it the other way. But adding here is actually easier, because the VAFs, they cancel. VAF plus a negative VAF is 0. So VAFs are gone, and you have 2 VBF. So what you get now is the 2's cancel, and what is this? VAO, so the initial velocity in A is equal to VBF, so VBF is whatever the initial was, and the initial was just VA. Oh, that's right, we're not doing this with numbers. So what happens then, if this is true, right, and VBF is VAO, then you so you solve for 1. So what does this mean for the second one? So VAO equals VAF, and then we can plug in another VAO, right? Because VBF is VAO as well, and so we move this over and we get 0. So VAF equals 0. So what does this actually mean? It means the first ball is not moving after the collision. So what happens is you have A, it's moving, it hits B at rest. Afterwards, A doesn't move, and then B moves off at the original velocity. And I don't know if you've ever seen billiards, but this is exactly what happens. If it's in an elastic collision, the more elastic it is, the more you can get the ball to hit the first one, and then it stops completely and gets the other one moving. Your elasticity of that collision determines if that happens or not. And I think they can like angle the ball in a very specific way to like make that work. But yeah, you're just transferring the momentum through that ball. So it hits, boom. Okay, and that's what happens. So that was before, that was after. I know mathematically without numbers it's kind of a mess. It looks complicated, but that's what the math tells us. Okay, and it's true, right? So pretty cool, pretty cool. Okay, so we've got 2 problems yet left, and unfortunately there are most complicated problems. There's a 2-dimensional one that we're going to do, and then there's one that is and then there's another like this one, which is kind of a lot, but let's see how we do it. So a projectile of mass 0.08 kilograms is fired into a large block of wood of mass 5 kilograms, and it's suspended like a pendulum as shown below. So let's go ahead and draw this for you. So before the collision, after, oops, okay. It's like it lets me move it one way and not the other. Okay. Oh my god. Okay. So the projectile is kind of like just like typically a bullet in this case. So before, we'll use MB, I guess. It's moving at VB. And we have this mass of wood that's just suspended. And then afterwards, what happens is the bullet suspended within it, and so this is MB plus the mass of the wood, so mass of the bullet plus mass of the wood, and it's a certain height, h. Okay? So what happens is, as a result of the collision, the pendulum and projectile swing up to a height of 10 meters. And we want to know what was the initial speed of the bullet to make it go that high. Okay? So you basically take the bullet, shoot it in, and then they swing together. Okay? So there's a lot going on here. But because we're not told it's an elastic collision, the first thing we want to do is assume it's inelastic, right? So we have our before and our after. Initially, this mass of wood's not moving, right? Not moving at all, but this guy is. So your initial is just MB plus VB. Our final is going to be this guy. So right after the collision, it's going to collide, and then it will move. Sorry, I forgot to draw that for you. That. MB, because they're moving together just like the trains, MB plus MW, and they're moving at V final, okay? Because they're going to move that way, and then they'll slowly, so we're just assuming it's this direction, then they'll go up. So we're going to treat it like a one-dimensional problem. And now what we need to do is we need the initial, whoops, I don't know why I added those. Sorry, it's mass times velocity for momentum. So we need the mass of the bullet. What was the initial mass of the bullet to cause this? So I'm going to go ahead and do VBO. Yeah, I'll do VBO. Okay. So MB VBO equals MB plus that times V final. So VBO equals MB plus MW over MB times V final. Okay, so mass of the bullet. Do we have that? Yes, right there, the projectile. And we have the mass of the wood, 5 kilograms. So we've got that. So that covers these guys. But do we have V final? No. We still need so is there a way where if we knew the height, we could get velocity? Yes. After the collision takes place, there's no more loss of energy. So what we can do is we can use energy to pull this off. So use energy. The KE, so the kinetic energy of the mass of wood plus mass of bullet equals the gravitational potential energy at max height. So 1/2, the mass is both of them, V final squared equals MB plus MW GH, right? Because all of the collision, or all of it going into it. Okay, so after the collision takes place, the bullet's fully embedded, and it's now moving at velocity v, and all of that energy goes into how high it goes. One question you may have is why couldn't we just skip the step and say, well, the mass of the bullet moving at VB, and use that kinetic energy into the height? The reason is when it collides with the block of wood, you lose energy. And so we can't just do a direct energy conservation problem here because you're losing energy when it collides. You're using it to when it embeds, right? There's friction, there's heat being released, you're deforming the wood in some way. So it's not just straight energy that you can use for this. Now, if you had how much energy was lost from the system during that collision, you could do it. But because of that, what we have to do is do momentum conservation, which we can always do even if we're losing energy, right? Then you do energy conservation after the collision takes place. So we can go ahead and cancel the total mass here because this guy's the same. And remember, we need to solve for V. Do the same thing we always do. Multiply that 2 over, take the square root, 2gh. So now our VBO is equal to the ratio of that, so MB. So now we plug in. So now plug back in. So we had our MB plus MW over MB, I believe, times our V final, but our V final is square root of 2GH. And now we can plug in the numbers and make everything work mathematically, or work numerically. So 0.08 kilograms plus 5 kilograms over 0.08. 9.8, 10. And what you end up getting is VBO equals 889 meters per second. So it needs to move pretty quick to propel that mass of wood upward. Okay. So again, for this problem, because we're losing energy here, we can't just do a straight conversion from the initial energy to the final energy. We have to go through momentum. And so we do before and after the momentum. Okay. And then we use the height that we know to solve for that final velocity just after the collision. Because at that point, all the energy's already been lost from the system, and so no more energy loss will occur. Okay. The final problem is again billiard balls, everyone's favorite. Okay, and this is our 2D momentum problem here. Okay, so billiard ball A is moving at speed 3 meters per second, and it strikes a ball at rest of equal mass in an inelastic collision. After the collision, the two balls move off at 45 degree angles from the x-axis, with ball A being plus 45 degrees, ball B being minus 45 degrees. And we want to know what are the speeds of the two balls after the collision. Okay, so let's go ahead and draw this. So you have the before and you have the after. Okay, so you have billiard ball A, and it said it's moving at 3 meters per second. You have ball B, which isn't moving at all, 0. After the collision, it says that ball A moves off at plus 45 degrees, and you have ball B also moving off at 45 degrees, but minus. At this point, for a 2D problem, you should set up, here's VBF, we don't know it, and VAF, and we need to know it. You should set up a coordinate system. So I'm going to do, set up coord. I'm going to do just a standard XY Cartesian. So for 2 dimensions, we need to preserve or conserve momentum in both dimensions. Conserve in both dimensions, okay, that we've established. So in the x direction, we have P initial in the x equals P final in the x. The initial in the x is A is moving along the x-axis, right? So it says 3 meters per second. So what I'm going to do is I'm going to say MVAO in the x direction plus 0 because the second ball wasn't moving, and this will equal P final. Now, we need the x direction of these movements. We don't know what VAF and VBF are, but if they're moving off at 45 degrees like this, we need cosine of that angle to get the x direction. So this will be MVB final, or VA final, sorry, it's ball A in the x direction, okay, plus MVB final in the x direction. And so if we want to write this out, it would be MVAO, because it's fully in the x. So we don't have to do anything with that. That would just be cosine of 0 degrees, which is just 1. These guys would be the VA final times cosine of 45 degrees. I'm running out of room. Let's move. Except this would be minus 45 degrees. And so that gives us our directions there. Now, the masses. I haven't been using subscripts because they're all of equal mass. And because they're of equal mass, we can just cancel these guys. So we have VAO equals VAF cosine of 45 degrees plus VB cosine of minus 45 degrees. And that's our x equation. Our y equation looks pretty similar. Poi, as it were, or pfy, however you want to say that. So we have VAO in the y direction, and then here, with our masses, MVA final y plus MVB final y. This would be MVAO sine of 0 degrees, which this is 0. MVA final sine 45 degrees. And then this one would be plus MVA final sine minus 45 degrees. Let's move this back left. Okay. Once again, the m's all cancel. More than that, this guy's just 0, because sine of 0 is 0. So we don't actually have any momentum in the y initially. And if you look at this, I mean, nothing's moving in the y. Makes sense? Here we have VA final sine 45 degrees plus VA final sine minus 45 degrees. This is our y. So these are our 2 equations so far. So now we need to solve for VAF, whoops, and VBF. These should be B's. How long did I make that mistake? Okay. So we need to solve for VAF and VBF. Ooh, what the heck? So we need to solve for VAF and VBF. Okay. I'm going to start with y equation because it's easier. Okay. So we have our y equation. 0 equals VAF sine 45 degrees plus VBF sine minus 45 degrees. By the way, I should mention, once you get to this point, it's basically all algebra and how good you are with tricks at this point. You've kind of done all the physics. It's kind of like forces, right? Once you have your x and y equation, or forces, so in forces, once you have your x, y equations, the rest of it's just algebra, albeit a lot of complicated algebra. So I'm going to try to simplify this as best I can. Sine of 45 degrees is root 2 over 2, if you remember your trick. And this guy, do you remember even and odd functions? So this is an odd function. And so an odd function is a function where if you have minus 45 degrees, this is equivalent to this, where you can pull the negative out of the angle. That's how it that's the reason it's an odd function is how graphically it looks about the 0, the y-axis, and how it's reflected about that as a function graphically. But what it means mathematically is we can just pull this negative out. Okay, these two things are equivalent. So, which means for us, we can plug in that negative root 2 over 2 here. Okay, so I'm going to rewrite this as 0 equals VAF root 2 over 2 minus VBF root 2 over 2. And now what I'm going to do is I'm going to add this to the other side, so you get VBF root 2 over 2 equals VAF root 2 over 2. These cancel, and what we're left with is VBF equals VAF. Okay? And so that means that the final velocities are the same. We don't know what they are yet, but they're the same. So the final velocities are the same. Which makes sense. If you're shooting a billiard ball at another one and they move off at the same angles, the only way for that to happen is if they're moving at the same rate. If they have the same mass, of course, and they do. Okay, so same mass, moving at the same angles, they must be moving the same rate afterwards. So now plug this, so now call VAF and VBF just VF, because now they're the same. Plug into X equation. Okay, so now we have to look at the X equation. Okay, our X equation was this, so I'm going to do this now. So I forgot to have an F up here. Okay, so VAO equals VA final cosine 45 degrees plus VB final cosine of minus 45 degrees. Okay, so I'm going to rewrite it. So VAO equals VF plus VF, just replacing these because they're the same thing now. All right, so now we could add these, right, together if these were the same thing. But the problem is cosine of minus 45 isn't the same thing as 45. Or is it? So this is an even function. Which means cosine of minus 45 degrees equals cosine of 45 degrees. So if we want to rewrite this, we can now rewrite it again. So that's handy. Just some tricks. You'll notice that in physics or in math courses, you just kind of pick up little tips and tricks like this along the way to solve things mathematically. But it definitely is challenging for sure. Oh yeah, I forgot to mention I did cancel all the masses. So this guy, oh, I forgot to put 0. Oh, no, wait, it's not 0, sorry. I don't know what I'm doing. Okay. So, VAO equals V final, I'm going to rewrite this now as root 2 over 2, plus V final, root 2 over 2. So now we can add these. It's literally half plus half, it's 1. So VAO equals V final, root 2. So now V final, we can finally solve for it. V final, which equals VAF equals VBF, right? They were the same, is the initial velocity times, or over root 2, sorry. We need to divide that over. So this equals 3 meters per second over root 2 equals 2.1 meters per second. So this was a very long problem. I mean, look how much math there is, right? And that's the case when you have something two-dimensionally. You can imagine if you have something two-dimensionally and elastic as well. There's just a lot to think about mathematically and algebraically when you're taking care of that. But also notice this type of problem, right, where, you know, some of the stuff is canceled, right? This initial velocity was 0. The masses were the same. If you didn't have that and you had it be elastic, it would be an extremely long problem. But nevertheless, this is still a complicated problem, and you should spend time learning it. Okay. But yeah, I hope it made sense. I'm not going to make this video go any longer. It's already an hour long. Thanks for watching, and stay tuned for the next one. And I'll see you later.